So yeah, so this is a high-level architectural diagram of the Tintri operating system. It shows kind of the basic components in the system, how they're related. We're going to just leave this up here to give kind of a feel for the components in the system and to serve as kind of talking points for the particular components or things that you're particularly interested in. But before we dive into this, I wanted to first address one question of sometimes we're asked, well, how Tintri manages Flash, for example, different from adding a cache to Flash as a cache to an existing storage system. So just wanted to provide a little information on that. So if we look at how people often add Flash to existing storage systems, you have some number of disks on your underlying system, and they typically add a modest amount of Flash, kind of mostly as a read cache. Right. And because it's kind of a read cache, all of the writes that come into the system eventually have to end up on the disk. So there's a lot of writes that come into the system. They go down to the disk. And then what the Flash does is it absorbs a certain fraction of the reads. So it's providing a large number of reads, some of which is coming from the Flash and some of which is coming from the hard disk. And in some systems, they have an additional optimization where some of the data that's being written to the system is also kind of written to the Flash as well, so that you don't suffer misses on every first read from the system, right? But the fundamental thing is that the disks are in the primary data path, and all of the data actually ends up on the disk at some point, right? So as the performance of the Flash scales, it becomes faster and faster. It's only really accelerating the reads. It's not accelerating the writes. Right? What we do at Tintri is very different. What we started out with is basically designing a file system specifically for Flash. So the Flash is kind of the primary tier of storage in our system. All of the writes go directly to Flash. Right? And of course, the reads come almost entirely from Flash as well, over 99% for the vast majority of workloads. And a lot of the data simply lives and dies within the Flash system itself. It never goes out of the Flash, doesn't go to the hard disk. But what happens over time is that certain VMs get powered off, people create snapshots, they replicate data, and so on. And it doesn't really make sense to keep snapshot data, replicas, powered off VMs, very cold parts of VMs, on the Flash because it's so very expensive, right? It's hardly ever going to be accessed. So what happens is that over time we notice that some of these data is not being accessed, and we write that small part back out to disk. And a lot of the data we write out to disk then is never read again because you create the snapshot for data protection purposes. It gets expired, it gets deleted. The data in the snapshot never gets accessed again. So even a smaller fraction of the data that we write to the disk gets read back again in case it's accessed. So the timescale we're talking about is basically given the current dollars per gigabyte of Flash and the dollars per IOPS of hard disk, the data that is going to disk are the things that are not accessed in the last day or two. So anything that's accessed more frequently than say at least once every day or two is all going to end up in Flash. So the stuff that's going to disk is really the really cold stuff that is not accessed even on a time scale of a day or two. And of course, as the dollars per gigabyte of Flash becomes cheaper and the dollars per IOPS of disk essentially remains flat, that time interval is going to become larger and larger. Right? So this is a big distinction between designing a storage system specifically for Flash that's designed to get essentially Flash level latencies for all of your I/O versus say adding a Flash as a cache to an existing storage system and getting only like say 50% cache hit rate. Right? If you're getting a 50% hit rate, you still have I/Os that take 6 to 8 milliseconds, something like that, taking into account queuing for disks and so forth. Whereas when you're getting 99% and higher hit rate for Flash, you're essentially getting sub-millisecond Flash level latency. So it's a very big difference.
So with MLC, how are you maintaining the endurance problem? It's not even eMLC, it's MLC, right?
Yes, absolutely.
Yes. So the the log structured file system does part of the job there. It makes the job of the drive to wear level easy by making the drive see big sequential I/O, and that's one of the things we actually qualified on our drives is how much sequential I/O do we have to do to just make the underlying garbage collection turn off. That there's no internal write amplification on the drive, so the drive lasts longer than it's sort of spec'd to, even because it's not doing the normal internal work that they assume.
And of course the inline dedupe and compression really help a lot as well. It's very easy to get at least 4x dedupe and compression. So most of our customers get at least 4x, and if you have a lot of clones, then you could get even higher values like 6x, 8x, or even higher. So 4x, you could think of it as kind of a base, very safe level of compression that you can get.
Is that combined compression? And
yes, that's correct.
Combined.
So total data reduction. And so if you combine all of that, we basically engineered the system so that even under very, very heavy write workloads, the flash will have a lifetime of at least 5 years. So given the engineering techniques we've applied, the endurance of the MLC flash is really not a significant issue.
So it's really more like sub-1 tiering than it is like caching.
Yes, you could almost think of it as tiering in reverse. Like, when people think about tiering in primary storage, they think of the data going to disk, and then the hot stuff be moving to flash. We're kind of exactly the opposite.
Right.
We put everything in
the
flash.
The location is flash, and
Yeah.
if it turns out to be cold,
Yeah.
it's demoted.
You could even
What's the granularity you're moving things at? The VMDK?
no.
So we use, because we were designed this way from the start, we actually use different block sizes on disk and in flash. So the flash block size is 8 kilobytes, and that's really if we ever have to pull something back in, or we can decide to do it at that level, or if part of a larger block is hot and part of it is cold, we can send just the cold portions down to disk, where we're using a much larger 500K block size.
Yeah, and we tried both 8 kilobytes and 4 kilobytes. Looked at various ranges, and for us it worked a lot better. Yeah, and NTFS block size is 8. Exchange Server SQL, they use 8. So for us, the 8 worked a lot better, especially once you start offering a lot of virtualization functions like snapshot and cloning and so on. Just the amount of metadata you have to manage can become very large if you're not careful.
And what's the ratio of flash to disk?
We have about 2.4 terabytes of raw flash and 13.5 terabytes of usable hard disk space. So the usable capacity of the system is 13.5 terabytes, and we have 2.4 terabytes of raw flash, which after dedupe and compression, you get some additional leverage on that.
And Tintri is primary storage for virtual machines, right?
That is our goal, yep.
Yeah.
And you've got inline, software, dedupe, and compression.
Yes.
Yeah. And
everything goes to flash.
Yes.
That's correct. Now, one other thing referring to the block size. The block size is very important, of course, for managing flash, because if, for example, you were to move data, in chunks of say a gigabyte instead of 8 kilobytes, that gigabyte would have to be accessed at least once a second before it's viable to be kept in flash. I mean, at that point, it's cheaper to store it in flash than to serve the IOPS from disk. But at 8 kilobytes, that 8 kilobyte block only has to be accessed once every day or two. So we're able to keep a lot more of the hot data in flash by using this large, smaller chunks.
Granularity is something people don't pay enough attention to when they look at auto tiering.
Yeah.
You mean auto-tiering an entire LUN is not useful?
Yeah.
Between SATA and fiber channel.
Yeah, but there's a lot of more conventional systems that are moving multiple megabytes based on the heat.
But they're very big systems, and how can you map? So if you've got like a petabyte in a storage array, how much working cache would you need to be able to map that if you broke it to 8K?
You need lots of CPU.
Or you need an
It's just one of the reasons why those architectures don't work that well with flash.
Yeah, fair enough.
Yeah, and this is, I think, a realization that many people in the industry is coming to. Basically, you're taking something that's existing, you put flash on it. That system is not going to scale linearly with improvements in flash. If you design the system so that it's primarily designed to work from flash, and then maybe you're using the disk to store basically like backup data on the disk. Then this is going to scale perfectly with future improvements in flash technology.
How do you achieve inline compression and dedupe without caning performance?
So we do a couple things. Obviously, we have NVRAM in front. That means we're not as latency sensitive on how long it takes to do the compression and dedupe. We're designed from the ground up to be multi-core. So as CPUs continue to scale to more cores, we can take advantage of that and stay on a good curve there. We keep our dedupe in memory. We're not taking an extra flash read to do a dedupe. We have to make some trade-offs there, but we found that's what works best.
Which also explains why we can't add more disk shelves.
Yeah,
that's part of the reason we have the scale-out model we do. But we also believe in that scale-out model because that's the way virtual environments work. When you run out of CPU, you don't pull the rack out and plop another CPU in there. You add another shelf unit and add that to VMware vCenter to start loading new VMs on there.
yeah. And there's also actually a positive performance benefit of doing inline dedupe and compression, because you do pay a little extra CPU up front in order to do the dedupe and compression. But once that's done, you have a quarter of the data you had coming in. So you have a lot less data that the rest of the storage system actually has to handle.
Exactly. That gets back to the flash lifetime, that if you have to pick this data up and rewrite it at a later date, you're doing write amplification to save space, which doesn't make a whole lot of sense. You might as well get it right the first time.
Right.
Can you turn off compression and dedupe?
No.
So it's fundamentally part of the architecture rather
I mean,
than a
we
cannot
could turn it off.
Okay.
Customers cannot.
Yeah.
Right.
How
So-
much NVRAM?
About a gigabyte.
I think it's a gigabyte in this one. Yes.
It's just happened to be a convenience size that came in the card that we're using. It doesn't actually require a gigabyte, but that was kind of the unit that it was available in.
Yes.
Yeah.
Right, and why go smaller if it comes that way?
Right.
So one of the things that is important here is that we use a lot of CPU. We assume that CPU is a relatively inexpensive resource.
Right.
So can you give an idea in terms of in our box what the processing power is?
Absolutely. So we are currently using 2 sockets, quad core, actually that was the 445, and then with the 540, they're hex core CPUs. And right now we have plenty of spare CPU cycles, which our upcoming replication feature will use some of that. So we're relying on CPU power scaling as we add additional functionality, as well as kind of scale the size of the system as well. So right now the CPU is not a bottleneck in our
The
system.
Xeon 5600s, right?
Yes, the Nehalem class. Yes.
Yeah.
So at this point, I'd like to go back to here and just give you a brief overview to open up additional discussion topics. So just kind of starting from top down, basically, as Kieran mentioned, our system is hypervisor agnostic. It is not designed specifically around VM or anything like that. We plan to support other hypervisors, relatively soon. Today, we do support mainly only VMware because that is where the market is. So, but in the future, it could be VMware Zen, Hyper-V, KVM, etc. And of course, some of these hypervisors are going to use protocols other than NFS. NFS is the current protocol that we support. Hyper-V, for example, will be supporting SMV. Also, VMware has announced a new protocol called vVolumes, for example.
Is that what they're calling it?
vVols or VM volumes. Those are the 2 words that we've heard.
Evolve?
vVols, yeah. And to us, they're just storage protocols. They're protocols for accessing storage. In the case of something like vVols, it's better. It has a better match with virtual machine workloads. So that's going to allow us to make our VMware functionality, provided in a better integrated way with VMware. But obviously, even if you have the protocol, you still have to implement the functionality, all of the per VM functionality you need in order to support the protocol, right? So just having the protocol is not going to change everything overnight. So the system is accessed through these protocols, and it comes to a layer which we call kind of the protocol manager. And this is the layer that takes these protocols which operate at the level of files or even LUNs or what have you, and it internally converts it all to operations on virtual machines and virtual disks. So within our file system itself, we operate basically at the level of virtual machines and virtual disks. This means that for every I/O request we get into the system, we know exactly what VM or vdisk generated it, right? So this is what allows us to maintain and measure statistics on a per virtual machine, virtual disk basis, right? With a traditional storage system, doesn't know anything about virtual machines or virtual disks once you get into the storage layer. So it gets an I/O request, it knows what LUN is associated with, it knows what volume is associated with, but it doesn't know what virtual machine or virtual disk generated it. So when you ask it, well, how long did this virtual machine take to access the hard disk in the system, it doesn't know, because it doesn't know how to tie a request to the virtual machine or virtual disk that generated it. Right? And
That's really the demultiplexing concept that VMware was talking about when they talked about vVols.
absolutely, and that's one of the big improvements that protocols like vVols will allow people to do. And then once it comes into our system, we have quality of service built in throughout our system. So one way to think about it is, VMware also has lots of quality of service features like storage I/O control, storage DRS, all of those type of things. But those features primarily control queuing of requests into the storage system, right? So they're kind of like metering lights on the freeway, right? They control access to the freeway. But once you get on the freeway, if you don't have preferential access lanes, you just get stuck behind everyone else. You end up competing for resources with everyone else on the freeway. So you may be able to get onto the freeway quickly, but if you don't have the preferential access lanes, you get stuck on the freeway once you get on the freeway. So what we're doing at Tintri is building in those data highway lanes or preferential access lanes so that different classes of traffic, like different virtual machines or virtual disks, can get different levels of service in the system. And we're building that as a fundamental part of the Tintri architecture or file system. Right. So once it gets assigned to lanes, then it goes through the dedupe and compression engines that we just discussed earlier. And the great thing about it is a lot of data comes in here and a little data comes out there. And so once you're done with the dedupe and compression, the file system is operating on a small fraction of the data that's actually written to the system. Right. And then the file system itself then has features built in like snapshot and cloning, per VM vdisk monitoring, performance isolation, so that your throughput intensive databases don't trounce over your latency sensitive desktops. Working set.
So we can assign per VM quality of service?
Yes. I mean, the basic thing we provide, first of all, is just isolation between VMs so that one VM doesn't interfere too much with other VMs. But we also provide mechanisms whereby the user can provide feedback. So if they want, they can give another VM more resources than it would normally get.
Can I give a VM less resources than it would normally get?
Today, no, but we plan to support that in the future.
Okay.
Yes. And the important thing to point out here is that all of these features operate at a per VM, per vdisk level and are built into the file system. So they are very robust. They take advantage of the dedupe and compression that's done. And they are going to scale both in terms of the size and performance as our storage appliances scale, right? They're not just added on as a layer, then incur additional metadata overheads or things like that. They're built into the system and they fundamentally leverage all of the fundamental data structures that we built in to do dedupe and compression. Right. And then, of course, we have an underlying
So
RAID.
when you say it scales out,
Yeah.
is there any connectivity between one Tintri system and another Tintri system? I mean, maybe management layer, or is that?
Right. Today, there's no such connection.
No data.
Later this year, however, we will be producing a management virtual appliance, which will be designed to manage multiple Tintri appliances. So that will give a single pane of control for monitoring and managing all VMs running on any Tintri appliance you have at a particular site or even across sites. Our model of scaling fundamentally, however, is not building like a clustered file system that stripes virtual disks across many nodes. It's more kind of like the virtualization model that VMware has, where if you run out of host resources, you can add additional hosts into the system. They're managed within the VMware's distributed namespace that vCenter provides. Similarly, if you run out of capacity, you can add additional Tintri data stores. You can run storage DRS over them if you want. And in the future, we would probably also provide additional functionality to maybe automate some of the decisions about load balancing and so forth. So, I mean, most VMs, remember, are not like huge. You don't find like a petabyte VM or something like that. So far, this model of scaling has been working very well.
So if you wanted something over 13 terabytes, there'd be no way?
Yep. You could not have a single vDisk that was over 13 terabytes today.
The largest ones that we've seen with customers have been 2 terabytes, and the usual size is on the order of between 20 and 40 terabytes.
Gigabytes.
Sorry, that would be interesting. Is the usual size that people have, and it's pretty consistent.
Yeah.
So just to remind everybody, the largest vDisk you can actually create today is a 2 terabyte minus 512 byte vDisk. The largest data store you can create is 64 terabytes. Caveat that with NFS has never really had that size limitation on the data store side. So you certainly can have more than 13.5 terabytes of Tintri, but your building block is a 13.5 terabyte data store. Think of that appliance as a data store appliance. We certainly have customers who have multiple Tintri appliances, and they've got their data store consolidations cut by maybe 13 to 1. If we see a customer's got a standard 1 terabyte data store in their environment, every one Tintri gets rid of 12 of their data stores.
But there's no back-end connectivity
No.
between the two. There's
No.
everything is on the front end.
Yeah.
That's
If you're
correct.
going from one to the other, it is just over the same network layer.
If you're moving data between them, it's
Yes.
through VMware, via storage
Through VMware.
vMotion.
Okay.
Right. We're not directly doing any sort of clustering below that. Although we will have replication as a VMstore to VMstore efficient copy.
And
So
if
it's a
you could-
loosely
and if you could
coupled.
tie that into storage DRS, that would be cool.
Yeah. Well,
If once storage DRS can support sub-millisecond latency as well, then yes.
Yeah, but just to have storage.
Absolutely,
Have storage
absolutely.
DRS tell you to move it rather than
Yeah.
Yes.
do a
Yeah,
storage
exactly.
motion.
The last components here, these are little snippets from our GUI basically, but I drew them in here to illustrate the fact that they are you should really think of them as fundamental parts of the storage system. Like they're not just a storage management layer or a pretty GUI that we've slapped onto a more traditional storage system. What the GUI is displaying here is information that is available only because the file system itself is VM aware and knows about virtual machines and virtual disks. So for example, one of the things we have is what we call an end-to-end latency breakdown. And it tells you for each VM what the total latency of accessing storage for that VM is, but also it breaks out that latency into individual components. And you will see this very clearly in the demo. So for example, it tells you all the way from the guest operating system level how much of the latency is incurred, for example, in the hypervisor itself, the green bar, or in the network sending and receiving the data, the yellow portion of the bar, or within the Tintri file system itself, the blue bar. And if you are suffering flash misses, how much of the additional latency is incurred because you are going to hard disk. And this information exists only because the file system itself is VMware. Another unique thing that we have is what we call a performance fuel gauge. Basically, most storage systems tell you how much of the capacity is used on the system and how much capacity is remaining to be used, but they don't tell you how much performance is used on the system and how much performance is remaining. And oftentimes, customers don't discover this limit until they add that final VM, and it causes IOs to miss in the cache or whatever, and the performance of the system goes off a cliff. Right? We provide a very clear indication of that, and producing this itself actually is a significant effort. Actually, maybe Mark, you could describe a little about how we do performance reserves.
Sure. So there are two main contributors there. One is, how much flash do you have remaining? Is the working set still fitting in flash, or are we spilling out of it? And the other is just the throughput limitations of the box itself, because we are software-based. We can only handle up to a certain number of IOPS. based on the how fast we can access flash, how fast we can do the dedupe and compression.
Yep.
So we actually look at the histogram of how hot the data in flash is. If we've got a lot of cold data, if we've got a lot of blocks with very few accesses, then we can say, great, those could actually be going to disk tomorrow, even though if they're going to flash today. And they're not really stressing the system. Whereas if we've got a lot of blocks with a high access frequency rate, even if they're a small part, even if we haven't filled up the appliance very, very high, flash is at a premium. And we would indicate that by saying those VMs and that system is very heavily utilized. So we put those two components together, how hot flash is, how much capacity do we have left in flash bytes and disk IOPS on the back end, combined with how many front-end IOPS we support through the controller to give an estimate of how many more VMs could you put on here. If you're at 33% performance capacity, add a new VM. You're not going to experience a problem. Once you get up to 100%, that next VM is going to start causing other things in the system to slow down and experience higher latency.
Right.
If you guys could get flash at the same cost of disk, would you replace all your disk, or is that something
Yes, absolutely. If the cost per gigabyte of flash was lower, we would use all flash.
So some of the other full SSD arrays that claim that they have done that, what's kind of your take on that?
But they claim that based on the fact that you're doing compression and dedupe on flash, but not compression and dedupe on hard disk. I mean, you can compress and dedupe both disk and hard disk.
Although you pay a bigger read penalty on dedupe data from the disk.
Yes, but on the other hand, you have some amount of flash to absorb that performance.
Not necessarily, depending on the unit of your dedupe and the dedupe method you use versus your read size.
So our architecture can support all flash if we wanted to.
Yes.
We just today what's the difference, the multiple between flash and disk?
Yeah, so flash is currently say about $2 a gigabyte MLC flash, and SATA is maybe around 10 cents a gigabyte.
So it's a factor of 20.
Yeah. So this is not something we have a religious position on. We just use hard disk today because that is the most cost-effective way to provide the capacity people need to hold their VMs. Because it doesn't help if your flash is giving you, hundreds of thousands of IOPS if a customer cannot buy enough flash to hold the VMs that they want to run. So we just do it because it's a cost-effective thing to do. As soon as the dollars per gigabyte of flash or hard disk shifts, we would also shift the ratio of flash and hard disk that's in our system. And at some point, we would probably get rid of hard disk altogether. So this is why our storage system is fundamentally designed as a flash-based storage system. It can actually operate perfectly fine without any hard disk. Yeah.
I guess where I was going is that some companies say that they've already done the cost ratio.
Okay, but the same technologies they apply to flash, to dedupe and compress, to get it down to
$10 a gig, $5 a gigabyte, whatever.
$5 a gigabyte is the number most of them use.
$5 a gigabyte can also be applied to hard disk to get it below 20 cents to.
In fact, Data Domain applied dedupe and compression to hard disk, got say 20x compression, and therefore their cost per gigabyte was, I don't know, like 0.5 cents per gigabyte.
Yeah, but you guys are conflating $5 a gigabyte system cost to me with component cost to you.
Right.
So
it's more of a relative argument.
The argument we're just making is relative. That as long as there is a gap, we can move both of them down by doing compression.
I buy that, but I think Dwayne's question is more. Those guys say they'll sell me an all-flash system for what you'll sell me a hybrid system for. Why should I buy a hybrid system? And so we're just talking about cost to consumer, not cost of components.
Right.
Are they lying? That's the question.
Well,
we are open to a yes.
We'll see what the prices are. We'll see what the prices are when these products are available. The other thing you should note is that today
their availability is this available?
Yes,
Okay.
we've
'Cause
sold a
not
bunch
all
of them.
are.
They're already
Yeah.
Okay.
already
So
there.
So just an idea in terms of that. So we launched last year. So we've been in the market for a year. We have 70 customers, and 90% of them are in production. Our largest deployment is one where on a single system, a customer is deploying 800 VMs. Most of our customers are deploying hundreds of VMs actually, which is something that's actually surprised me. So we have many customers that are actively using our system today. And
Yeah.
they're in finance, they're in technology companies, they're in education, they're in state government and so on. So this is real, and this is being used with large
And,
numbers
and
of
if I
customers.
remember right, MSRP is like $60,000 a system, right?
That's for the T445. This is the 540, which is, I think
19K.
this, yeah.
So basically, if somebody says, man, somebody watching this says, man, I love this, and I want to go get me some of this Tintri, they need to have a check for 60K or 90K.
So being
Okay.
the lone field guy here, I will answer this one. I think the best way to look at it is if you want that unit over there with 3 years of 4-hour support, list price, not street price, 137,000-ish for 3 years of 4-hour support for that. And Howard, to your point, I think when you look at our design goal of 99% reads and writes out of flash,
Yeah.
and then you compare the all-flash vendors, which are 1% more than that, and you look at our dollar per workload cost, which is really what we are trying
Right, no,
to go after.
but that's just the math I'm
Right,
doing.
right, no,
And
no.
so you guys,
Yes.
are in
So-
the $7 to $9, and the guys who aren't shipping yet are claiming they will be in the $5, and your 7 to 9 is before data reduction. So it's about 2.
We're actually, the important metric is actually dollars per how many VMs you can actually run on the system. So if you look at our systems, you can run 1,000 desktop VMs on the system, which gets us in whatever it is. You can do the math there on what the cost per the list price is.
It sounds like $9,
$90. Yeah.
If you stick to round numbers, then that's
90.
easy.
So, and then you can run 500 server VMs, up to 500 server VMs on the system. If you compare that with an existing system, which would be a modular mid-size array, then what we do is a very good deal.
Oh,
So-
no question, but
Yeah.
but the topic of discussion at the moment is comparing you to the all solid state guys.
Yeah, but so those.
And the answer to the question is you're still less than half the cost, and will deliver 90+% of the performance.
And remember,
And that's a
that
big
they
enough
can-
story for us.
They can support hundreds of VMs because they don't need atomic test and set, which none of the small guys are going to have.
Right.
Yeah. So the other thing to keep in mind is that this unit is a fairly constrained packaging. There's actually only 8 SSDs and 8 hard disks in the system. And if you're doing RAID 6 plus spare and so on, that's quite a significant overhead as well. So all of those economics are going to improve very rapidly. We will also be doing dedupe band compression on the hard disk in the future as well. So all of those things are going to improve, obviously. Yeah. Yes.
If you're running 800 to 1,000 VMs out of that single machine, how does that get me to bandwidth? What's the backend connectivity?
Backend connectivity is
No, the
10
front-end connectivity.
The front end, the storage
To
storage
stream
area
1,000
network
VMs?
is 10 gigabit Ethernet.
How many?
It's a bonded configuration, so and the controllers are active passive. So
Active standby.
Active standby. I love that.
active standby, yes.
There's a
So you
reason
have
there's a-
1 gig,
there's a-
1 gig active.
10 gig.
10 gig.
Oh,
10
10
gig.
I'm sorry, 1 time 10 gig.
Yes.
Fully duplex too.
It's not iSCSI, it's NFS, vVols, or SMB?
It's NFS today.
Right now it's NFS.
Yeah, because the secret sauce is in the file system. If you go iSCSI, you lose the secret sauce.
Exactly, because the
We-
SCSI protocol is gonna obscure what's going on above it, and you lose all that information, and then you need something like, you know, VAAI to try to send some of that information along, but it's still smoke signals.
Right.
I mean, NFS is the only way you're going to get enough information.
And it still doesn't tell you, well, this is this file name which came from this VM, so I know what to do with it. It's all
Right.
about context.
Yeah. I mean, actually, we believe that you can also build the same set of functionality using iSCSI, but it is additional work in order to do that. Yeah.
Well, you'd have to spoof contents and.
Yeah.
Well,
we have access to the
you'd
management
have to
APIs
interpret.
on vCenter, so we can get all of that information to do the mapping and so forth. Yeah. But obviously, it's a lot easier if you have something like vVols. Then at least you don't have to struggle with the mapping. You could focus on implementing
Right.
the functionality. Yeah.
Yeah.
Somebody's asking what the failover time is for the passive controller.
The failover time,
Standby.
yeah, it's engineered to have a worst-case failover time of about 30 seconds.
And
Oh, that's right up there with the SMP timeout.
and what's an average?
Average is load dependent. Is the answer that typically
30 seconds is worst case.
30 seconds is worst case.
Yeah.
Often we see 10 to 15.
Yeah, and
Or-
that's
or
that's of
less
course for an
even.
uncontrolled failover where you like just pull the, you know, controller or the controller goes poof. If you do a controlled failover, then it's a lot faster.
When you're saying failover, you're talking about the two internal controllers within the system there?
Yes. Yeah. The bonded Ethernet pair switches over a lot faster on link failure.